Assalamualaikum warahmatullahi wabarakatuh. My name is Atika Syaidah binti Arzainul, and this is my team member Siti Nur Arbaiyah binti Apandi, Muhammad Numan bin Khalid, Muhammad Hamizan bin Muhammad Yazid, and Abdul Munir bin Muhammad Yusuf. Okay, today I would like to present about cruise control system. Okay, for the first is what is cruise control system and why is it important? The function of a control system is to change the system behavior that is performed over time in a particular desirable way. For instance, in view of potential hill or adverse wind, we may want the speed of a car on the highway to stay as near as possible to 60 miles per hour. Or we may want an aircraft to follow the desired altitude heading independent of wind guide and velocity profile. Or we may want to maintain at desired level the temperature and pressure in a reactor vessel in a chemical process facility. All this can be achieved by control method today without human interference, which is called as automated control system. This control involves the element of controlling the quantities, for example speed, altitude, temperature or voltage, in which this element need to function in desirable manner over time. Okay, the objective is to evaluate the performance of different classical control scheme P, PI and PID for cruise speed system.
For methodology of the cruise speed system, the first by using Simulink software. The step 1 is to open the Simulink, then create subsystem to define all block. Step 2 by define all block for input, sum, integrator, gain and also the output. Step 3 is to connect the input, sum, gain, integrator and output all together. Step 4 by connect and add gain or damping to make it as a closed loop. All of this block will be defined in the subsystem. Step 5, after finish define all the block for the subsystem, we connect the subsystem with step block, sum block, discrete PID controller block and lastly scope block. Step 6 is by making the system as closed loop. Step 7, input different value for P, PI and also PID at the block discrete PID controller based on the value selections. Step 8, to create the coding in MATLAB so we can run the Simulink by insert the value of M, B and also U. Step 9 is by click on the run button to run the code in the MATLAB. Step 8, after we run the code in the MATLAB, we can run the Simulink program. Step 11 is to run the Simulink program to generate the Simulink graph. As in the table, we will gain the value for the controller parameter and also performance and the robustness. And all the steps of 1 until 11 is repeated for all value of P, PI and also PID. The second software is by using MATLAB software. The first step is to generate the MATLAB code by input the desired value for P, PI and also PID. Okay, the next step is to run the MATLAB code by clicking on the run button. Step 3 is to determine the graph characteristic, and all the steps is repeated for all value of P, PI and also PID.
Assalamualaikum, my name is Muhammad Hamizan bin Muhammad Yazid and I will be continuing to explain result and discussion for cruise control. Okay, first for proportional gain, when we increase the proportional gain, it will have effect on the control signal. So the control signal also will be increased at the same error level. Next, for consequence of rising proportional gain is that the steady state error appears to reduce but not disappear. Next, for the derivative, adding a derivative word to the controller improves the controller ability to anticipate the error. Second, the control signal will become high with derivative control if the error continues to slope upwards, even though the magnitude of the error is still reasonably small. And lastly, introducing a derivative term has a little effect on the steady state error. Next, for integral, when we add the integral controller, uh, an integral concept appears to minimize the state error further. The downside is the integral term is that it may make the machine slower and oscillatory. So when the error signal change sign, it can take a sign to change the error signal. So here is our result for our project for cruise control. So we have two conditions. The first condition is the proportional gain is we set to 1000 and the second condition we set to 5000. Okay, so as you can see from the P2 table, when we only set the proportional gain for 1000, the rise time is 2.09 seconds and there is settling time and the peak is at 0.52. Okay, then for PI and PI2 is where we add the integral, the KI. So as you can see for proportional gain 1000 and the integral is 1, the rise time increasing, but there's no settling time and the peak also increase. While for PI2 we increase the integral. Okay, the rise time decrease and we have the settling time. Okay, and the peak also decrease for PI2, and this is where we start to add derivative. Okay, so for PI1 we add derivative 10 and PI2 we add derivative 50. So as you can see, the rise time increasing, but it's same for uh, the integral. There's no settling time, and the peak is maintained at 0.955. While when we adding more value for the derivative, the rise time increase and the peak also increase. There are no overshoot when we adding the integral derivative, the only and also proportional gain. Next, for the result to condition, when we set the proportional gain at 5000, yes, you can see at first when only have proportional gain, the rest time is 0.439 and there's settling time. Okay, but when we start to adding the integral, okay, as you can see for PI3 the integral is 40, for PI4 the integral is 1. Okay, as you can see there's not much difference for the rise time. There are different for the settling time. The PI3 is 0.881 while the PI4 is 0.907. There's no overshoot and the peak we can say it maintained. And when we adding the derivative for the condition 2, okay, as you can see the difference is not very much for rise time. PID3 0.453 while PI4 0.51. Okay, the settling time also does not does not have different. Okay, but for the second condition there's no overshoot like the first condition. So based on the project that we have done, we can say there will no overshoot for cruise motor even we change the value for P, PI and PID. The parameter that will change is the rush time and the peak for each crop. When the proportional gain value is higher, the rush time will be quicker and the settling time also will be faster. And lastly, if the proportional gain value is low, the cruise motor power output will not stable. That's all for me. Thank you.
Assalamualaikum. My name Abdul Munir bin Muhammad Yusuf for my ID number FB17089. Now I will present about the result and discussion about the DC motor. Now you can see the two tables. For the DC motor, system analysis is conducted based on different value of Kp, where Kp equal 200 and another one Kp equal 500 for the condition 1 and condition 2. Increasing the proportional gain Kp, the system steady state decrease, shown as in table 1 and table 2. The steady state for the table 1 will be equal 0.952 and for another one 0.98. For this one, it provides the larger peak amplitude and more overshoot for the system plus 1, where the Kp 200 overshoot will be equal to 38.2 and for the Kp overshoot will be equal 54.8. For the Pi will be Kp will be equal to 100 and Ki will be equal to 250. For the another one, Kp equal to 100 and Ki will be equal 500. That is steady state reference if will be equal value is 1, however is 1 have a negative effect on the speed of reaction and overall stability. Both the result show that the time which is time needed for the output to be achieved and to stay within specific error band after the input stimulus increase as the integral gain Ki increase, applying PI control will not decrease. The rise time and the increasing Ki value will guarantee overshoot as shown in table 2 39.7 and for another one 47.4. After that, for the PID controller has optimum control dynamic include the highest stability, short response time, zero steady state and no oscillation. The need to use the derivative gain KD part is addition to the PI controller is where its ability to predict the error decrease in overshoot. For PID1 and PID2, the table 1 and table 2 respectively show the zero overshoot. PID1 will show the zero overshoot and PID2 will be show the 8.23. When KD equal 1 and we will increasing the value of KD 10 show the overshoot decrease.
My name is Muhammad Mabekali, ID FA17008. Will continue the presentation regarding conclusion for these two projects. For DC motor projects, we compare the DC motor drive with and without the system feedback and stimulate drive under different load and speeds reference in a closed loop system. For a closed loop system, they wanted to have a fast response and zero steady state error. In this project, we increase the value of Kp and Ki, with result tend to reduce the system error but will worsen the overshoot and settling time and transient stabilities, while Kd in PID will balance out the overshoot and settling time. For cruise control conclusions, the role of control theory is to help us gain insight into why and how the feedback control system works with various designs and analytical issues. As the projects go on, and the proportional gain Kp, when the value is higher, the rise time and the settling time will be faster. If the Kp is low, the fast margin will also be low, then the output of the cruise engine will not be stable. That's all from us. Thank you.